Alright, so we ended the last lesson talking about what should we set RL to be for max power transfer. So that's the objectives of this lesson here, is to discover what we should set RL for maximum power transfer. And the way we're going to approach this, we're actually going to go to an even simpler circuit here. We're going to have some voltage supply, which I'll just call VS for voltage supply. We're going to have just some resistor here, and then we're just going to have a single resistor, and then we're going to have our load here. So it's a two-circuit element, very simple one, because there's something we can do. If we can answer this question, believe it or not, knowing what we should set RL to be is going to make life easier for us. Okay, so let's see here. What do we got here? Well, let's again here think of this as being the voltage across the load. And we could get the voltage across the load to be equal to, well, it's just going to be voltage division RL over R plus RL times VL. I'm not VL, VS. Okay, so we've got that. Now we're going to do my power computation here. So the power for the load is going to be the voltage of the load squared divided by the load resistance. And that's correct, but I'm actually going to do this when I was just thinking about this. I'm going to do this where we know that really the definition of power is current times voltage, and I'm going to do it that way because we can get the current of the load very easily. The current of the load is simply, because this is a series circuit, VS divided by R plus RL. So now what I'm going to do here is I'm going to use this equation for power, and then these two here substitute in, and we get here then that the power for the load is going to be RL over R plus RL quantity squared times the voltage source squared. Now, what we need to do here is we need to analyze, this. For a given problem, R and VS are fixed. And then we would actually, the way you would do this is you would use calculus, which we're not, since many of you haven't had calculus yet, and even if you had, it's not really worth our discussion to go through all of the details of the calculus. It's really reserved for a calculus class. We could use calculus to determine what RL needs to be for max power transfer. And the short answer for this here is that for this circuit that we have, RL needs to be equal to R for max power transfer. So let's look at that circuit with actually some specific numbers here and see why that works here. Just with a couple pieces of data here. So we'll do a simple 10 volt. We're going to do a real simple circuit here. 5 kilo ohm resistor. And then, okay, well, what should RL be for max power? RL for max power should be 5K. So let's go ahead and do that. So let's put in, for part A, we're going to let RL equal 5K, and we're going to get the power of the load. Now, with this being 5K, this is a really easy problem. I'm going to let this be 5K here. I'm going to just do it in red here off to the side. If I think of this as being the load voltage, this is simply going to be 5K over 5K plus 5K, voltage division, times 10 volts, which I picked all these numbers just to be really easy and nice for us. So we get 5 volts. Okay, very simple voltage division there. And then the power of the load would simply be voltage of the load squared divided by the resistance of the load. So this would be 5 squared divided by 5K, which I believe gives you 5 milliwatts, but let's double check our computations here. Yep, we get 5 milliwatts for the power. So I'll just put that here. Power is 5 milliwatts. Now, sometimes people's temptation is to say, yeah, but if I put a larger resistor in here, we know that there's going to be more voltage dropping across this. And yeah, you'll get more voltage, but remember, power is not just about voltage, it's voltage and current. And also, in our equation that we've been using here, if you increase the size of the resistor, well, yes, the voltage might be increasing, but the resistor is also increasing. So both of these numbers are increasing. So that doesn't mean we're going to get a larger number. So let's look at a quick example with that. Let's let RL even just be 4 kilo ohms. So I'm going to erase this here, and we're going to do this with 4 kilo ohms. And so if I do this with 4 kilo ohms, we know that the voltage for the load, it's all the same equations, it's just I'm going to have 4 in here now for the load. And you get 4.44 volts roughly. And then the power for the load then would be 4.4 volts, 44 squared, divided by 4 kilo ohms. Which, if we do that, let me redo my computation here. I did something wrong here. There we go. You get, and not just rounding, I'm going to carry out, you get 4.9284 milliwatts. So I am actually getting less power out on the load. If I had 5K, I got 5 milliwatts on the load. With 4K, I'm only getting 4.9. And you can do 6K to convince yourself if you think, well, wait, if I put a larger resistor in there, I'm going to have more voltage. You won't get more power, though. The maximum power is when RL is equivalent to this resistor here. Now, to finish this video, we need to ask ourselves a question is, well, what about more complicated circuits? And I'm not even going to draw a very complicated circuit here. I'm going to do something that's actually pretty straightforward here. We should ask our question now is, what should RL be in this case? And it turns out that it's going to be something that when we did in some previous videos, that you can kind of see why we maybe did some of these things. It turns out that for max power transfer, RL should be equal to R equivalent. So we'll have to find the equivalent resistance of this circuit, and that's what we should set the load to be in order for max power transfer. And remember, we did find equivalent resistance of circuits before. That's honestly why we were doing that. It should be R equivalent. Now, I want to say one additional thing here. This is often related to a concept called Thevenin equivalent or Norton equivalence. So if you have your text, you'll probably see something in reference to Thevenin and Norton equivalence. If you're looking for some more things to read and just learn more about circuits, I encourage you to look at some of those, but we are not going to take things quite at that level. But if you want to think where that comes from, basically, if we go back to this circuit here, and I were to kind of look at just this to the right here, to the left here, this resistor, this would be like a Thevenin equivalent of some more complicated circuit. But we're not going to actually need to find the Thevenin equivalence for what we're going to be examining in this course. We're just going to need to find the equivalent resistances, which we'll talk about how to find these equivalent resistances in these kinds of situations.